Good evening, everyone. Welcome to your class of Introduction to Measure Theory. This is the third lecture, the first part of the third lecture, in which we will talk about a concept that is called uniqueness of measures. So this concept is motivated by the fact that it's in general difficult to prove or to show when do two measures, let's say we have some measurable space here, this is our space and this is our sigma algebra, and we can associate with this measurable space two different measures, let's say mu and some lambda. So how do we prove that these two measures are equal? Well, without the concept that we will develop today, this will require to show that for every element of the sigma algebra, both functions are equal. So for sigma algebras that are bigger or that have a lot of elements, these will in general turn out to be complicated or to be difficult. So the concepts that we will address today will give us an answer under certain conditions in which we can guarantee that these two measures are the same measure, and that is that they are equal. So that's why the title of today's lecture is called Uniqueness of Measures. So to do this, the first concept that we will propose today is the concept, the definition of a lambda system. So we say that, as always, we start with a space that is non-empty. This is a non-empty set. And we have some collection. Let's say instead of our usual A, let's go with some symbol like this. This is a collection of subsets of X. So this is a subset of the power set of X. Now we say that this collection is a lambda system if and only if three properties are maintained. So the first property is that the empty set is in this collection. The second property is that if we have some countable family in this set, such that this is a increasing sequence. So let's write here, this is increasing. This is increasing, and that means that this holds for every n. Then the countable union of all of those sets is an element of this set. So it is similar to what we had in sigma algebras, but now it is restricted entirely to increasing families or increasing sequences. So it is clear that any sigma algebra will hold these two conditions. But let's see what happens with the third condition. We have any pair of elements here, such that the first is a subset of the second, then B minus A is in this set. So once again, this is kind of a more restricted property of sigma algebras, because in sigma algebras we didn't need this characterization. So this property holds for every pair of elements of the sigma algebra. In lambda systems, we need to have that one is a subset of the other to have this difference in the lambda system. So we can write this as a remark, and that is that every sigma algebra is a lambda system. The converse is not always true, so not every lambda system is a sigma algebra. And it is clear because if, let's say, we have the second property, this only holds for increasing families. So if you have a non-increasing family, we can have at least not necessarily that the countable union of the elements of the family is still in the set. Also with the third, if we have two sets that one is not included in the other, so let's say that two sets with non-empty intersection, then the difference, this part here, won't be necessarily in the set. So we cannot say that in general every lambda system is a sigma algebra, while it is true that every sigma algebra is a lambda system. So we have now a proposition. And that is that if we have a non-empty space and some family in the power set of X, then there exists a minimal lambda system that we denote by this symbol. Let me highlight it here. Lambda of F, well, with capital letter lambda, like this, that contains F. So this is of course totally equivalent to the definition of the generated, or the sigma algebra generated by some family. So this now will be the lambda system generated. So let's word the proof. The proof will the flow of the proof will be the same, or well, really similar to proof of algebra, in which we define some set, then we prove that this set is non-empty, and then we conclude that there is some intersection or some union. This is customary in algebra. This is the usual work, so we will do it like that. So let's define some set of lambda systems such that this is a lambda system of X, system of X, and this family is contained in the lambda system. So then, as I told you, the next step will be to show that this set is non-empty, that this is different from the empty set. But to do that, we need to recall that we had a trivial sigma algebra that was the power set of X, right? So since every sigma algebra is a lambda system, then this power set of X will also be a sigma algebra, and of course the power set contains F because of the condition, or well, the definition. So we have an element in the set V, and that will guarantee that this set is non-empty. So given that this set is non-empty, we can use it as an index set for arbitrary intersections. We don't know if this set is countable or uncountable, and we don't really care. We can do just some arbitrary intersection of elements in the set V, and we will denote this as the lambda system generated by F. So we will need now to show that this intersection is a lambda system, but this is kind of easy to do because the empty set is in every, let's write it here, for every lambda system in V, the empty set is in every lambda system by definition. Then the empty set is also in the intersection. And the second property was that if we have a couple of, an increasing family, right? We have an increasing family that is countable in this intersection, then so if this countable family is in the intersection, then it will also be in every sigma algebra, right? So this then implies, and this is increasing, let me write it here, this is important, this is increasing. So since this is also increasing because it is the same, and we will have that its countable union is in every lambda system, and since it is in every lambda system, then it is also in the intersection of every lambda system. So that proves the second property. And for the last property, let's suppose that we have a couple of elements in this intersection, and one of is a subset of the other. So if this happens, it's just the same. If it is in the intersection, then it is in every lambda system. And with this property, this means that this proper difference is in the lambda system for every lambda system, then it is in the intersection. So that concludes the proof that this is a lambda system. So this is a lambda system, and it is also the minimal lambda system, because if we suppose that there is another lambda system, let's say lambda star, such that is included here, and that includes the family, the arbitrary family, then this will imply that this lambda system is an element of V by definition of V, and then this will imply that this is a subset of this lambda star, because the intersection is a subset of every element of the set of indexes. Then that will show that they are equal. So that means that this lambda system is in fact the minimal lambda system that can contain the family F. And that concludes the proof of that proposition. So just to make it clear, we say that this symbol is the lambda system generated by F, where F is a subset of the power set of X. Alright, so moving into the next property, let's go with this proposition. So as always, we have an empty space. Now we have some lambda system. This is a lambda system of X, And additionally, we have that X is an element of the lambda system. And we have that for every pair of elements of the lambda system, the intersection is also inside the lambda system. So if these two additional properties of the lambda system hold, I mean additional besides the three properties that define a lambda system hold, then this is a sigma algebra. So this is the connection of the final connection. I mean, because you know that every sigma algebra is a lambda system, but we talk about how lambda system may not necessarily be sigma algebras. Well, now if the lambda system holds these two properties, then now it is in fact a sigma algebra. So this is important. Let's do the proof here. You know, to do this, we need first to recall the definition of sigma algebras. So let's write it in this box here. We had three properties. The first one was that X was an element of the sigma algebra, and of course the zero property was that the space was non-empty, right? Then the first was this. The second was that for every pair of elements in the sigma algebra, we had that the difference was also in the sigma algebra. And the third was that if we had an arbitrary family that was countable in the sigma algebra, then the countable union was in the sigma algebra. Need more space. This was on the sigma algebra. All right, so lambda systems. A lambda system hold also three properties. The first one is that the empty set is in the lambda system here. The second is that for every pair such that this is a subset, then this difference is in the lambda system. And the final was that if we had an increasing, let me highlight that, increasing family, then its countable union was in the sigma algebra. So now we append a couple more of properties, and that is that the whole space is also in the lambda system, and now intersections are held inside the lambda system. So we will see how this now implies these three properties. The first one is of course hold, right? Just right out of the definition of, well, of the property here. So we will work out the next two properties. So for the second property, we will do it slowly here. We want to show that arbitrary differences are held inside the lambda system. So let's say we have two cases. In the most general sense, oh well, we can do it in three cases, perhaps this. So as always, doing graphs helps a lot. This is case 1, this is case 2, and this is case 3. So this is A, this is B, this is A, this is V, and now this is A and this is V. So we want to show that the difference of A and V, well, we have another case now. A and V, case 4. So we want to show that the difference between A and V are in the lambda system. So in case 1, the difference between these two, A minus V, so whatever is in A that is not in V is of course equal to A. So this holds. Case 1 is solved. Now case 2, we have a non-empty intersection, so A minus V will be this part of A, but this intersection here is an element of the lambda system because of the second property here. So besides that, this intersection is a subset of A. So the difference between this set will be inside the lambda system by definition 2, by the second property of the definition of lambda systems in general. Then this difference is in fact A minus B. So with this, the second case is also solved. And now in the case 3, A minus B is the empty set because, you know, A is included in B. So the empty set is always an element of lambda systems by definition. Definition 1 here. So this case is also solved. And the final case will be A minus B whenever B is a subset of A. But this follows straight out of the definition, point 2 of the definition of lambda system. So this case is also solved. So in every possible case, the difference is in the lambda system. So check mark there. And now we will do the last property, and that is, let's suppose that we have some countable collection of elements of the lambda system, and we want to show now that this union is inside the lambda system. So it is kind of obvious what we should do here, because we want to transform this into some increasing family, so that we can apply the definition 3 of lambda systems. So the thing will be that to show that this is a family of our lambda system. So Vk will naturally be the union of every aj from 1 to k. So this clearly implies that this is an increasing family. What is not totally obvious is why should this set be an element of the sigma algebra? Because, this is of course a finite union of elements of the sigma algebra, but we don't really have that here. I mean, if we have some, let's write it like this, for v1 is of course true, right? So this holds, but let's say v2 is equal to a1, the union of a1 and a2, and this is a1 and this is a2. So how we go from here to show that the union is also an element of the sigma algebra? So let's review what we have here. We have that differences are inside the sigma algebra whenever, we had it in general also. So for this we need to recall that differences are in fact complements. And what I mean with this is that let's write it here. We had that the space is an element of the lambda system, right? So since differences are held inside the lambda system by what we previously shown, then we have that this difference is inside the lambda system, but we can write this like the complement of A in X. Let's put it like that. So complements are held inside lambda systems. So now we have that intersections are held inside by this property. So we can write this, in general, from here we can write this thing as the complement of intersections of complements. When you apply that complement, the intersection becomes union, and every element takes its complement, and the complement of the complement is the same set. So now we have intersections, and you know that from here intersection of two elements are held, but we can conclude that any countable intersection is in the lambda system. You do this just by induction. So this thing here, because complements are maintained in the lambda system, this inside the lambda system, then this will also be inside the lambda system, and once again complements are held inside. So every element here is an element of the lambda system. So this is the step that we had to take. So now we have this proven, this inclusion proven, and the family is increasing. Also, this union is equal to the union of every vk. This is kind of easy to see, by the way it is defined. And then this implies, by the definition of lambda systems, that the union of increasing families are held inside lambda system. So this shows why the union of arbitrary families inside the lambda system are held inside it. And so this is the last step in the list of conditions to guarantee that the lambda system is a sigma algebra. And that concludes the proof. Now, we conclude this first part of the lecture by showing another definition. Let's say that we have some family in the power set such that the whole space is inside a family, and that for every pair of elements of the family, the intersection is held inside the family. Then F is called a pi system. So what we did previously was, in fact, to show that a lambda system that is also a pi system means that, it is also a sigma algebra, because the elements, the conditions of the proposition were exactly the definition of pi systems. So this is a pi system. Right. So this is the heart of what we did previously. That if some collection or some family is at the same time a lambda system and a pi system, then it is a sigma algebra. So we will conclude this first part of the lecture here. If you have any questions, you can write it down so I can answer them in the following. And then we will continue with a theorem, the important theorem of uniqueness of measures in the following video. So see you around.